All right, teachers, let's go. Let's go ahead and get into our chapter 14, last chapter of the semester. How about that? Okay, so let's go ahead and get into this. All right, so hopefully this goes straight on here today. Get this here. Don't know why this keeps doing this to me, but there we go. All right, so let's try this now. Didn't want to do that all the way through. There we go. All right, chapter 14, transformations. Okay. So some of the things we're going to be going with, what a transformation is, okay, isometries, and then the types of transformations, a translation, a rotation, different types of rotations, and then we're going to also talk about tessellations, okay, and the different types of tessellations, which this is a chapter that is a very good chapter for you guys in terms of the smaller kids, younger kids, things they can do, not a lot of numbers math as much, okay, and you can be creative, you can be colorful with this kind of stuff. Some of the terminology, yeah, you might use, might not use. It's good to have them started on it. All right, so we're going to talk about what an isometry is, okay? So it says any rigid motion that deserves length or preserves length and distance is isometry. A translation is one type of isometry. So we're going to be talking about moving figures around. Okay, those are transformations. Certain transformations do not change size and how far the, how big the figure is. Okay, it keeps size and shape. In other words, the figure stays congruent. Okay, it just moves. Okay, and those are isometries. Okay, there's a few other transformations. There's another transformation does not keep size. We do that in another section of this chapter. All right, so any function from a plane to itself that has a one-to-one correspondence is a transformation of that plane. So all the transformations we talked about will have a one-to-one. Okay, we'll talk. You'll see that as we label things on how for every point it has its own exact same one point. Okay, because transformations are functions, they have properties of functions. So let's talk about a translation. The common term for a translation is a slide. Okay, so if you want to use the word slide, you can also use the word slide. Okay, so and some people will, and some kids will do this. Okay, they'll tend to use that as a term, but you can use a slide, but that is not a mathematical term. Okay, so a translation is a motion of a plane that moves every point of the plane a specific distance and a specific direction along a straight line. Okay, so what we're talking about here is, here I have what they call a pre-image. Okay, it is your original image. Okay, we're going to translate this person or slide this person down the slide in which you have your image. Okay, now to be a translation, you must know a specific distance. Okay, that is given to you by what they call a vector. The vector here goes from here all the way down to here. And the distance goes from the beginning of the arrow to the tip of the arrow. Okay. Now, a figure and its image are congruent. Notice the kid does not change size. It is the same child at the end of the slide. The image of a line is a line parallel to it. Okay. All right, so let's go ahead and erase some of this. Get out of this page. All right, now I'm not going to have you construct a translation, but it is good to know, and I could show you a way here how However, what I do want to stress to you here is the image we always label as A prime, the little dash up here. That's A prime. The pre-image is A. That's the original. Okay. Now, when it comes to moving something, okay, here we have our slide arrow, or our vector is the proper term. That means we are going to take AB here and slide it or translate it a distance that far. That's the distance we want to send this. Okay. Now, to do that, okay, there is a way you can do this. You take a piece of paper, okay, you draw your line, okay, so you draw your line AB, okay, then you also draw a vector. How far do you want to translate that that distance? Then put another piece of paper on top of it and trace it. Find AB on top of that paper, trace the AB on top of your paper with a pencil. Helps to have a pencil, okay, and also trace the arrow, the vector, and then slide it until the top paper, until M here, M touches N. Okay, so you slide it that far. Okay, then retrace AB on top of it. And what will happen is the bottom, the underneath of the top paper will have picked up some carbon. Okay, and when you push back down on it, it will leave a residue of a line here, which you can copy. Okay, so that would be A prime, B prime. Now notice how they label it, A prime and B prime. Okay, and we would now have the shape from A prime, B prime to, and this is what I want to do here, we would now have A prime, B prime. Okay, and that's what you're left with. All right. All right, now one thing you can use is dot paper. I'm a big fan of dot paper. It's lovely. It has a great advantage to it. This is square dot paper. You want to find square dot paper, all you got to do is Google square dot paper or dot paper, and it'll give you all types of different dot paper, and just make a print of it. All right, it says find the image of AB. Here's AB. We want to find its image if it's translated from X to X prime. Picture it on the dot paper. So notice they give us here in red the vector. So we want to move AB, the segment AB, this far. In other words, it's 2 diagonals. So you're going to take A and B, and we're going to slide it 2 diagonals. So it's going to go 2 diagonals here, 2 diagonals here. Or you can go down 2 over 2. Whoops, sorry, clicked it. Down 2 over 2, down 2 over 2. And now notice I have A prime, B prime. Okay, the image of each point of the dot paper can be obtained by first shifting 2 units down and 2 units to the right. If you have, now if you're using square dot paper, you can use your diagonals too. Okay, a lot of times it might not go 1 diagonal at a time, so you might have to count down and over. All right, so how do I show the coordinates on a translation? Okay, if I want to move the point A here is at -2, 6, B is at 0, 8, and C is at 2, 3. Okay? We want to move by using a coordinate system, and in this coordinate system, you're going to give you a coordinate with a plus and or minus in here. And it says we're going to add 5 to the x value and subtract 2 from the y value. In other words, I'm going to do this vector. We're going to move it 5 to the right, which is adding x by 5, and bringing it down by 2, which is subtracting 2 from the y. Okay, and so what you can do to find your new points, your image points, A prime, B prime, C prime, is add 5 to all the x values and subtract 2 from all the y values, and you have your new A, B, C prime. So it slides this way, and that's the term of the translation. Okay? Now, what you should have on here, what they don't have, is that A should be prime. Oops, let's do this a different color. We should have A prime, B prime, and C prime as their labels. Okay? Because that now shows you where your image is now at. And it also tells you where you began and where you ended. All right, so a translation is a function from the plane to the plane such that every point xy corresponds a point. Remember, there are one-to-one correspondence, that every x value gets added an a amount and every y value gets added a b amount. Now remember, a and b could be negative, so that means you'd subtract. Okay, this can be written as a coordinate xy moves to, this arrow goes moves to. Okay. I'm going to wait for this for a second.
One nation under God, indivisible, with liberty and justice for all. Honor the Texas flag. I pledge allegiance to thee, Texas, one state under God, one and indivisible. Please join me now in a moment of silence to reflect and think about how you can be the difference.
The joys of me working from school.
Just a couple of reminders. Again, I reminded you of this last week. Some of you still.
Let's continue. Sorry about that. All right, so I'm too far into this. I'm not redoing it. All right, so notice this arrow means it denotes moves to. So every x gets moved to a new value by adding a, and every y by adding some b value. All right, so find the coordinates of an image of the vertices of this quadrilateral. So it works for any shape you want. So if I'm going to move xy to x minus 2 and y plus 4, I'm going to take a value, add from 0, 0, minus 2 plus 4. I would get a prime to be negative 2, positive 4. I'd add to b, which is 2, 2, to get 0, 6. C is at 4, 0. C prime would now be at 2, 4. And then D would be at 0, 2. Okay, so now I have this new point. Okay, so let's go back to that. Okay, so where would my new shape be? Well, let's look at that. All right, so I would now have from A, which is at negative 2, 4. So I would now have a point up here, negative 2, 4, to B, which would be at 0, 6. It would be up here somewhere. Okay, then I'd have 0, 6 to 2, 4. Something like that. And D would be at 0, 2. And then you'd have your square there. Now, of course, this is way off the grid. Okay, but you can get the idea of this would be at a prime. Okay, this would be at B prime. This would be at C prime. And then here would be at D prime. And you'd have your shape. Now, of course, again, it doesn't look very good because I'm way off the grid. Okay, so you get the idea. All right, a translation determined by the slide arrow from A, which has 0, 0, to A prime at negative 2, 4. Okay, well, that would be the same as what we just dealt with. Okay, I'd subtract 2, add 4. So if I take this one, I want to go from 4, negative 3 to 2, 1. Well, to get from 4 to 2, I'd have to subtract 2. when we get to -3 to 1, I'd have to add 4. So you would get the translation of x minus 2, y plus 4. Okay? And so here is that square image that we showed you a little bit ago. All right, a rotation is another type of isometry. Okay, a rotation, layman's term, is a turn. Okay, so you can use a turn for a while, then turn it to a rotation. It is a transformation that is determined by holding one point, the center, fixed and rotating the plane around that point. Okay, by a certain amount of in a certain direction. Okay, so here we're not only going to have a distance, we're going to have a direction. Okay, and we have a term that a lot of these kids might have to learn. They may have to learn what clockwise and counterclockwise is. Okay, they might not know. Okay, because they're not used to regular clocks. Now, how can you do it with a piece of paper? Well, it's really cool that this is you can take a paper, okay, draw your figure ABC and where you want to circle, you want to turn this around, okay? Then you would need a turn direction, a turn arrow, rotation arrow, okay? Now notice this tells you the degree here, doesn't give you the actual number, but gives you how far and which way to turn it. They want it to turn clockwise, okay? So if I draw that, and what I would do is on my paper, I would have this arrow, and I'd have this arrow. Okay, and I don't think I can do a curved arrow. Okay, and you would want to show that I want to turn it this direction. Okay, so what you would want to do, you draw that on one paper, then on top of that paper, you put another paper, copy the triangle, and copy the arrow here. And then you would pivot, putting your finger on the dot, the center O, and turning it until your top paper matches up down here. And then you can retrace your figure. And that is your new turn, A prime, B prime, C prime. Now there still is a one-to-one corresponding, and the shape still stays the same. Okay? So it is an isometry. All right, now how do I turn on dot paper? Well, here center is O. So center is O, and they want you to turn this around 180 degrees. Okay, now this gets a little trickier. As you turn this thing's going to have to go at 90 degrees basically. Okay, but notice the distance. There's a difference here. You do have to worry about this distance here. Okay, this has to turn 90 degrees. This here will have to turn 90 degrees. Plus, if you take B and you notice if this is 2 away and I turn it 90 degrees, it's going to catch up to here. It's got to go 2 away. So which means B prime is going to be right here. Okay. C, notice it's going to have this distance and it's got to turn 90 degrees. Okay, and look how far it is. It's down 3 over 1. So it's going to be down 3 over 1. So C prime is probably going to be way up here. Okay. So when you turn it, you now have A. So when you look at the distances, that's kind of important here. When we look at these distances, okay, if you look here, okay, there's that 90 degrees. And notice from here to here is a diagonal, and here to here is a diagonal. Okay, here you go down 3 up 1. This would be down 3 over 1 at 90 degree angle. There's that 90 degree angle. Whoops. There's that 90 degree angle. Okay, so that's why all that works as it is. So it's a little tricky, and it's also tricky to find those. And there is a question that you do have to find that center dot. Okay, where did it center around? Okay, it makes it a little tricky with it. Okay, but what you can do is try and figure out what the angle. You got to find that same angle for all 3 points. All right, a rotation of 360 degrees about a point moves any point or hence any figure onto itself. Such a transformation is identity transformation. In other words, if you rotate it around the center of 360 degrees, you're going to end up the same spot. A rotation of 180 degrees about a point is a half turn. All right, so that turn takes us to what's called a tessellation. A tessellation of a plane is the filling of the plane with repetition of figures in such a way that no figure overlaps and there are no gaps. Okay, so notice this has got the same lizard, different colors. Okay, and sometimes tessellations can have colors, which would have to, if it has colors, it's got to continue the shape. Okay, here we have the shape, and notice you can find the center of rotation right there. There's a center of rotation there, center of rotation there. You can see where it rotates. And inside here, you can see little bitty hexagon or big hexagons. Okay, but they cannot overlap and they cannot have gaps. All right, so tessellations with regular polygons are both appealing and interesting. I don't know if they're appealing, but tessellations with squares, notice you can have straight on top of each other, or you can have a brick style. That they would continue the tessellation throughout. You can have equilateral triangles. Okay, so here's equilateral triangles, and here are hexagons. Okay, notice it'd be like a tile floor. Okay, you could do the ceiling tiles in the classroom, the bricks on the wall. Okay, depending on what your classroom looks like. You can create a tessellation on a piece of paper by just giving them a rectangle, because that's going to tessellate. Cut out any shape and put it on the end, and this would continue its tessellation through. And you can just continue that shape over and over and over and over and over again. Okay, here's another one. Here's a equilateral triangle. They cut out this little shape, pivot it, turned it on here, and then they want to tessellate this. And notice here's what it would look like tessellation-wise, because it's starting from a quadrilateral. All right, so it says which regular polygons can tessellate the planes. Regular meaning they have to have the same angles all the way around. So here's our hexagon. Notice it would tessellate the plane. Okay. The key is they have to connect at a 360-degree angle. So with the hexagon, every interior angle, if you remember, would be 120 degrees. 120, 120, 120 makes 360. So it does tessellate. Okay. If we have 3 pentagons surrounding the vertex of a tessellation, the sum of the angles around in a pentagon, if you remember, is 180 degrees. Okay, or 108 degrees, excuse me. Well, if I put 3 of them together, I get to 324. You put 4 of them together, you'd be over 360, which means it does not tessellate. This only can add up to 360, no more than 360, no less than 360. It says, on the other hand, if we include a 4th pentagon, you would have way too much. So notice it does not tessellate. So what can tessellate? Okay, well, if you remember, measure of the interior angle of a triangle. What remember that is what 3 minus, or the number of sides. If you remember the formula, I gotta think of this here real quick. Okay, to find the measure of the interior angle, remember it is n minus 2 times 180, right? Divided by the number of sides. Okay, so, and that's what divided by the n. Okay, the whole thing divided by n. It's probably not the proper way of writing it. It should be what? That and that. Okay, so that gives you your angles. Okay, so 60, a square is 90, a pentagon's 108, a hexagon is 120, and then all these other ones, you have these other angles, right? So now knowing those, since a 360 divided by a number greater than 120 is smaller than 3, the number of sides of a polygon cannot be less than 3. No regular polygon with more than 6 sides can tessellate. In other words, if I go back to here, you can't get less than 3 sides to tessellate. So a hexagon would be the biggest you could possibly have. Well, out of those 4, which ones can add up with multiple angles, add up even 1 or 360 degrees? Well, we already know pentagon doesn't work. So only triangles, squares, and hexagons can tessellate. Oops. Okay. So when we go back to that, regular triangles. I keep doing that. Regular triangles, a square, and regular hexagons are the only 3 regular polygons that can tessellate. Now, semi-regular tesselines, which means you get more than one type of polygon. Okay, so notice here is a hexagon with an equilateral triangle. Notice any connection of vertices would have to add up to 360 anywhere you look at here. Okay, although there are only 3 regular tessellations, square, equilateral, triangle, and a regular hexagon, many tessellations are not regular. One factor that must always be true is the sum of the measures of the interior angles must equal 360 degrees. So notice, these are not regular pentagons, but they are pentagons. 5-sided figures, just not regular. But notice it does tessellate. If you look here, that would be 360. If you look here, this would be 360. So it does tessellate the plane. Okay? Then you have these 2. This says the following 2 tessellations were discovered by Marjorie Rice, and the problem of how many types of pentagons tessellate remains unsolved today. Notice these are all pentagons, just weirdly shaped pentagons, and they do tessellate. Okay? But it's just another way of showing some tessellation. Now, how can you use these kind of things in your class? Well, you can give them a tessellation, make them color it to keep the colors the same. Okay? You know, if this is going to be orange, you know, all these orange, all these blue, you know, you can just have them color the tessellations. And even these, okay? This is a good one, you know, red, white, blue, you know, red, white, blue, and find some sort of transition that they can make sure they try and color it, okay? And they can get that tessellation done and see their tessellation in color. So it's good for the elementary kids. All right, so that is all of that section. I know it's a long one. I hope this helped.